Good morning. My name is Yukiataka from Japan. The title is Machine Learning Analysis of Climate-Sensitive Cardiovascular Disease in Urban Region. In summer season, morbidity or mortality risk of heart and brain disease is increased by air temperature rising at a nation or urban scale. Meta-analysis from worldwide research found that the cardiovascular disease mortality in older people increased by about 3.4% per each 1 degrees increase in temperature. And cerebrovascular mortality also increased by about 1.4%. In Japan, deaths from all cardiovascular disease accounted for about 23% of all deaths in 2019. This is the second highest rate after cancer. The number of Japanese patients hospitalized due to uh, cardiovascular disease will double by 2035 compared with 2005. Therefore, predicting the occurrence risk of cardiovascular disease from weather parameters provides important information for future healthcare. In this study, machine learning techniques will be applied to predict the mortality risk of cardiovascular disease during the summer season. We chose the 23 wards of Tokyo as a target region, and ischemic heart disease and cerebrovascular disease as target diseases in this study. Ischemic heart disease correspond to the ICD-10 code from I-20 to I-25, while cerebrovascular disease correspond to that from I-60 to I-63. These daily diseases were used as a daily mortality risk in this study. This slide shows a schematic flow of our analysis. In this study, we used the data set of July and August from 2009 to 2019. First, we performed a log analysis to select the log features to be used for machine learning. We needed to find out which variables and how many previous days are important for mortality risk, such as daily maximum temperature on the day or daily maximum temperature on the previous 1 day, the previous 2 days, or previous several days. This is a carryover effect of high temperature exposure on mortality risk. The second identified important features are used in machine learning by the bootstrap method using the SHAP library. And finally, we hydrocasted the mortality risk of cardiovascular and cerebrovascular disease in the past period of 10 years from 2009 to 2019 using the light GBM algorithm of gradient boosting method in the machine learning techniques. In addition, we challenged the futures risk assessment by using the transfer learning method, where the model learned the dataset of Osaka City in Japan, which has a hotter climate in Tokyo. First result with log analysis feature selection by using the distributed log nonlinear model, commonly known as the DLNM, is shown on the next slide. These slides show the change curve of mortality risk with daily maximum temperature. The left panel is A, correspond to the response of ischemic heart disease, while the right panel is B, correspond to response of cerebrovascular disease. Here, the mortality risk on the y-axis are defined as having a base of 1.0, which is a minimum number of daily deaths. You can see that the mortality risk of ischemic heart disease here increased significantly, and its lag effect was prolonged with higher maximum temperature, daily maximum temperature. On the other hand, mortality risk cerebrovascular disease was not important for daily maximum temperature compared to ischemic heart disease. Consequently, daily maximum temperature from the day to the previous 8 days was selected as machine learning features related to only mortality risk of ischemic heart disease. The next results show feature selection and importance by using Shapley additive explanation called SHAP. After this implementation, the mortality risk hierarchies were performed by the light GBM machine learning with selected important features. Next slide summarize those results. A bar graph on the upper left shows the three most important features selected by the SHAP library. Daily maximum temperature on the previous 2 days, and the day maximum temperature on the day, and accumulated temperature above 30 degrees can explain the daily mortality of ischemic heart disease. The accumulated temperature above 30 degrees is an index of the integrated temperature increment when the daily maximum temperature exceeded 30 degrees. In particular, as shown in the lower scatter plots, the daily maximum temperature on the day and the previous 2 days strongly influenced the SHAP values when it exceeded 33 or 34 degrees. A line graph on the upper right show the daily variation in mortality risk from 2009 to 2019. The green lines correspond to the actual mortality risk, while the red line is the predicted risk by machine learning. In many years, rapid increases in actual mortality risk were found. The machine learning prediction will reproduce these rapid increases, and that suggested that the increased mortality risk was caused by the aforementioned high temperature high temperature event continued from 2 days ago. Next slide, this shows the same result but for cerebrovascular disease. Air pressure related variables are selected as important features to explain the mortality risk. There are the air pressure on the previous 40 days and the pressure difference between the day and the previous days. However, lower scatters plots revealed a weak correlation between the pressure difference from the previous date and the SHAP values. Top right graph shows the daily variation in mortality risk where the prediction accuracy, such as RMSE and MAE, was comparable to that of ischemic heart disease. But the increases and decreases in both actual and predicted mortality risk appear to be unclear when compared with those of ischemic heart disease. Finally, we attempted future projections for mortality risk of ischemic heart disease in Tokyo 23 wards. Climate scenarios under RCP 8.5 was assumed by using the three climate models output from CME5. In this study, the transfer learning method was applied to evaluate the mortality risk from period of from 2045 to 2055. However, because it needed to use inexperienced or unlearned high temperature in Tokyo, so we mixed the data set Osaka City, having hotter climate than the Tokyo. Ah, okay. Sorry, no time left. The result is stated briefly. The implementation results in that the daily mortal risk of ischemic heart disease in Tokyo would increase by 29% at the 95th percentile and 35% at 99th percent under the highest warming climate model in the period from 2045 to 2055 compared with the daily mortality risk simulated to the present era. But should be noted that this result does not consider future growth in older population. Thank you. This is summary.
Yeah, thank you very much. I think we come up with an important